All right, here's another application of factor and remainder theorems, and we want to find the values of k that makes x minus 2 a factor of x cubed minus kx squared plus 5x plus k. If we call this p of x here, that means that p of 2 needs to equal 0, because if in order for x minus 2 to be a factor of that polynomial, p of 2 would need to equal 0. So we just plug in 2 into this polynomial. So we'd have 2 cubed minus k times 2 squared plus 5 times 2 plus k, and we'd have 8 minus 4k plus 10 plus k equals 0. So if we move all the k's to one side and leave the 18 on the other side, we'd have 18, and then we have a total that equals so we'd have, did I do this wrong? No, I didn't. Is equal to 3k. So k would be 6. So 6 is the value for k that makes that work. All right, the next problem, we have a similar, it's the same kind of problem. Values of k that makes x plus 3 a factor of kx cubed plus 19x squared plus x minus 6. And if we call this polynomial p of x, that means that p of negative 3 needs to equal 0, so I'm just going to plug in negative 3 for x. So we'd have k times negative 3 cubed plus 19 times negative 3 squared plus negative 3 minus 6. So this would be negative 27k. Oh, this needs to equal 0. So negative 27k cubed, that's not k cubed, sorry. Yeah, delete that. Negative 27k plus 19 times 9 is 171, and then minus 3 minus 6 equals 0. So this would be negative 27k, and then 171 minus 9 is 162. So if we solve this for k, we'd have 27k equals 162, and this one is k equals 6 also. If we divide 162 by 27, we get 6. So these sorts of problems can come up. Here is another look at the factor theorem, right? If this is a polynomial long division problem that's been done, and if you don't believe this is right, you can pause the video and check. But we've determined that x minus 4 divides 2x cubed minus x squared minus 22x minus 24 evenly. What the factor theorem says then is if I just plugged in 4 into that original dividend, I should get 0. And indeed, that is what we get. Now notice what that corresponds to graphically, right? If I were to plug in 4 into this polynomial, I got a 0 out. So 4 is a 0. 4 is a factor of that original polynomial. Okay, so similarly here, the remainder theorem states a similar thing. So in this case, we've divided 50k cubed plus 10k squared minus 35k minus 7. We've divided that by 5k minus 4. And we ended up with a remainder of negative 3. Now, by the way, what this means is that I could write the quotient. The answer to this division problem was 10k squared plus 10k plus 1, right? That was the quotient without the remainder. If I wanted to add the remainder onto that quotient, I would say minus 3 divided by the original dividend. Sorry, the original divisor. Right? That's the same thing if I just was like dividing, say if I divided 10 by 3, well, it goes in 3 times and then there's a 1 remainder, so that's 3 and then plus 1/3, which is more commonly written as 3 1/3, right? Now, if we were to think about what k is for this problem, right? If we were going to plug in what is the value of k that would give me that remainder of negative 3, like using the remainder theorem, I would take this 5k minus 4, and whereas x minus a is the thing I would plug in, is the divisor before, and I would then plug in a, that's because x is equal to a if you set this equal to 0. So x minus a equals 0. If you solve that for x, you get x equals a. So in this case, 5k minus 4 is equal to 0. 5k would equal 4. So k would be 4/5. So k is 4/5. That's what I'd be plugging in, and I should get I should evaluate this and get negative 3. And you see that that's what happens. Now, what does this mean graphically? What this means graphically is that if I were to plug in an x value of 4/5, so this is in fifths here, so 4/5 would be here, I will get out, I should get out -3. Now notice the scale on this graph is a little different, but where that crosses the, where, like, when you go to the x value of 4/5 and you go down to see where it hits the graph, that should be at about -3 right there. And so that's what that means graphically. Okay, now there's another way to write a polynomial, and it's called nested form. This just by looking at this might seem completely unnecessary, but it's the foundation behind something that's really pretty important. Now, what nested form is all this is you keep factoring out an x until there are no degrees of the x, like there's no, the variable x has no degree higher than 1. So we look at these terms here, we factor out the x. Notice the +6 at the end is there the whole time. So if you factor an x out of the 2x to the 4th minus 9x cubed minus 4x squared plus 8x, you get 2x cubed minus 9x squared minus 4x plus 8, and that's times x. And you keep doing that until you get this nested form of this polynomial. Now let's look at an example of why this is significant. Alright, so let's look at this example here. If I wanted to evaluate, so p of x is equal to 5x cubed plus 6x squared minus 7x minus 3. If I wanted to evaluate that for 1, right, what is p of 1? Well, if I evaluate any polynomial at 1, it's going to be pretty easy because 1 to any power is just 1. But if it wasn't 1, say it was some horrible number, then I didn't know like what it to the third was. Like say the number was like 14, and I wanted to know 14 to the third power, and I didn't have a calculator. Well, I wouldn't do that. I don't know what that is. And so nested form, what it does is it boils everything down to really simple math. There's just multiplication, so this would be 5 times x, 6 times x, 7 times x, and then there's just addition, subtraction, and subtraction involved. There's nothing going on here. Of course, we follow the order of operations, but there's no exponents, and this is really helpful. Now, here's a question, right? If we evaluate a polynomial at p of 1, what's another, based on what we've been talking about, what is another thing like what's the equivalent of that? And we'll answer that question in a second. But first, when we evaluate this polynomial with 1, we see that the answer ends up being 1, and the math is all laid out right there. It's pretty straightforward. Now, all we were doing, again, was multiplication, addition, then multiplication, whatever that is, right? So we multiplied the first coefficient by 1, then we added the next coefficient, then we multiplied that by 1, then we subtracted that from 7, then we multiplied that by 1, and then subtracted 3 at the end. Now, let's divide this. Let's actually do this division, because the equivalent of evaluating polynomial p of 1 is just dividing by 1. It's dividing by x minus 1, right? This is the same thing as p of x divided by x minus 1. So let's actually do p of x divided by x minus 1. So we have 5x cubed plus 6x squared minus 7x minus 3 divided by x minus 1. So real quick, let's do this. We'd have x goes into 5x cubed, 5x squared times. So 5x cubed minus 5x squared. And so subtract. We'd have 11x squared minus 7x. That would be plus 11x. Then we'd have 11x squared minus 11x. Subtract. Here that would be a 4x, right? 4x minus 3, and then it will go in 4 times, so plus 4. 4 times x, 4x minus 4. Subtract, that would be 1. Now notice something here. This is very interesting. This 5 is the same as this 5. This 11 is the same as this 11. This 4 is the same as this 4. And the remainder of 1 is that remainder of 1. This is what we evaluate it for. That's the remainder theorem. Now this might seem trivial, but it's very important, because if we could somehow emulate this math, because look, this math showed us what ends up being the answers to this division problem. Wouldn't it be great if we could similarly simplify how we simplified evaluating a polynomial? Couldn't we also simplify the division of polynomials? And the answer to that is yes, we can. Okay, so that brings us to synthetic division. Synthetic division is an alternate to long division, and in almost every case it's preferred. There's just some limitations to it. It mimics the math of evaluating polynomial nested form, which is why we showed you nested form. And if we had a polynomial p of x and we divided it by x minus a, we use synthetic division with a. That a value is very important. Now, because it's x minus a, it's very common to think, all right, I'm just going to plug in negative a for my synthetic division. No, do not do that. It can help you by setting x minus a, set whatever that factor is anyway, and set it equal to 0, and then solve for x. And that's what you're going to use in your synthetic division. Now, here's some limitations to this. You must insert missing terms as zeros. For polynomial long division, we use it as placeholders. It's kind of optional. It's possible to do polynomial long division without those placeholders, but it's impossible to do synthetic division without the placeholders. This also only works for linear factors. We can't, for example, use synthetic division to divide a cubic by a quadratic. It doesn't work. And finally, there's this, because of how it works, if we had a fractional linear factor, so for example 3x minus 2, if we wanted to know what we were going to use with synthetic division, we would have the a value would be 2/3. But then we're going to get a product, we're going to get a quotient at the end, and we have to manipulate that quotient before we say what the answer is. So let's jump into the procedural part here of synthetic division. Alright, so we're being asked to divide 3x cubed minus 4x squared plus 5x minus 7 by x minus 2. So here's what we're going to do. We're going to take that 2, because right, x minus 2, that means a is 2. So we're going to take that 2 and we're going to put it in a little box. Then we're going to bring down the coefficients of our original polynomial. So the 3, negative 4, 5, and negative 7. Okay, now what we're going to do, this line here is basically an addition line. We're going to take that first polynomial, the first coefficient, bring it down underneath the line, and it's 3. Then we're going to multiply the 2 times the 3, just like we did in nested form, and we're going to put that answer right there for 6. So then we're going to take the negative 4 and we're going to add it to 6, and we're going to get 2. Then we're going to take 2, multiply it by the 2, and get 4. And then we're going to take the 5, add it to 4, and get 9. And then the 2 times the 9 is 18. Negative 7 plus 18 is 11. Now, we just divided a cubic, like a third-degree polynomial, by a linear polynomial. So our quotient should be a quadratic, a second-degree polynomial. And so what we do is we drop the degree of our original polynomial, which was a cubic. We drop it by 1 to make it a second-degree polynomial. And these are the new coefficients. So we had this 3 and this 3. We had this 2 and this 2. We had this 9 and this 9. And then the remainder, 11, is this. So the remainder sometimes is drawn in its own little box here. So let's do an example here by hand. Alright, so here's a problem where we're going to use synthetic division, and we're going to set it up where we have our little box and our line, and we're going to write in what we need. So if x plus 3 is my x minus a, that means a is negative 3. So I'm going to put a negative 3 in the box. Then I'm going to bring down the coefficients. So 1, and then, notice there's no cubic, there's no third degree term here. So because it goes from 4x to the 4th minus 3x squared, I need to put in a placeholder for the x to the 3rd term. Then I have a negative 3, a 5, and a negative 2. Okay, so then the procedure goes, I'm going to bring this 1 down, and I put 1 there. Then I'm going to multiply the negative 3 times the 1, and I get a negative 3. Then I'm going to add 0 and negative 3, and I get negative 3. Then negative 3 times negative 3 is 9. And so negative 3 plus 9 is positive 6. Then negative 3 times positive 6 is negative 18. Alright, and then 5 plus negative 18 is negative 13. And then negative 3 times negative 13 is 39. So negative 2 plus 39 is 37. Okay, so 37 is my remainder, but my quotient, the answer to the problem of what is x to the 4th minus 3x squared plus 5x minus 2 divided by x minus 3 would then be, so 1 x to the 3rd, because it was 4th, now it's to the 3rd, minus 3x squared plus 6x minus 13. And the remainder is 37, so I can write that as plus 37 divided by the divisor, which was x plus 3. And so that's the answer to that problem. Now that's like I hope you'll agree, a much quicker way of doing this than polynomial long division. You could check your work with polynomial long division if you're not sure if you're right, but I promise you, if you do this the correct way, it is correct. All right, let's try another one here. So again, we're going to set up our kind of little skeleton for synthetic division. And in the little box, because x plus 4 is what we're using as our divisor, that means that negative 4 goes in this little box. We'll bring down the coefficients, and notice this time we're not missing any, so it would just be 1, negative 2, negative 33, 18, and 216. And so we just keep going. So we start with by bringing down the 1. Then 1 negative 4 times 1 is negative 4. Negative 2 plus negative 4 is negative 6. Negative 4 times negative 6 is positive 24. So negative 33 plus 24 is negative 9. Negative 4 times negative 6 is positive 36. 18 plus 36 is 54. And then negative 4 times 54 is negative 216. So 216 plus negative 216 is 0. So this one, if we divided x to the 4th minus 2x cubed minus 33x squared plus 18x plus 216, if we divided that by x plus 4, we would get an answer of x cubed minus 6x squared minus 9x plus 54, and that's it. There is no remainder. So this would tell us that x plus 4 is a factor of that larger polynomial. All right, one more example here. So if 3x plus 1 is my linear factor, then and so 3x plus 1 is x minus a, that means I'm going to put a negative 1/3 in this box. Okay, so that means that I bring down my original coefficients: 3, negative 2, 5, negative 1, and negative 1. So let's do this math here. So this would be 3, then this would be negative 1, then this would be negative 3, this would be positive 1, this would be 6, this would be negative 2, this would be negative 3, this would be positive 1, so we get 0. So what this tells us then is that this should be 3x cubed minus 3x squared plus 6x minus 3. Now, if you think about this, this doesn't make sense, because what this is saying is that 3x plus 1 times this should equal this original polynomial. And right away you can see that it doesn't, because if I do the first multiplication here, 3x times 3x cubed, I'd have 9x to the 4th, which is not correct. So we have to make an adjustment here. If we have a fractional a value, if we're using this for synthetic division and it's fractional, we have to take the coefficients that we end up with and divide them by that 3. And so what we really have here is that 3x plus 1 times what would now be x cubed, because I take 3 divided by 3, minus x squared plus 2x minus 1 so this was the actual quotient when I do that division. So those two things multiplied together will equal the original polynomial. All right, so one last thing here. If I told you that there was three linear factors of this polynomial, 2x cubed minus x squared minus 22x minus 24, and I told you that one of them was x minus 4, could you tell me the other two? And so this is kind of where we're going here with all of this. Now, so let's just do that division, and we're going to use synthetic division because it's faster. So there'd be a 4 in that box, and then the coefficients are 2, negative 1, negative 22, and negative 24. And then we do this math: 2, this would be 8, this would be 7. 4 times 7 is 28, so negative 22 plus 28 is 6. 4 times 4 is 24, so that's 0. So we'd end up with this new polynomial of 2x squared plus 7x plus 6. Now, look, that's a quadratic, and we can use traditional means to factor that. So if we wanted to factor this quadratic, we would say that this looks like it's going to be 2x squared plus 4x plus 3x plus 6. So that's going to be a 2x comes out. We're left with x plus 2 plus 3 times x plus 2. So this factors to 2x plus 3 times x plus 2. So if I wanted to know what are the other two factors, well, it's this one and this one. So this polynomial could just as well be written as x minus 4, that's the original one we had, times these new two that we just came up with, 2x plus 3 times x plus 2. And so ultimately, the whole point of knowing how to do this division is to be able to factor really gross polynomials, because while this and this are the same information, this one here is much more useful for us when it comes to actually figuring things out, because from this, I know that there is a 0 and x-intercept at 4, there's an x-intercept at -3/2, and there's an x-intercept at -2, and those will be very important moving forward.